So my name's Juli Berwald, and I wrote the book Spineless, The Science of Jellyfish and the Art of Growing a Backbone.
Do you know why warm waters speed up jellyfish's metabolism?
So so it's not all jellyfish. So every species is adapted to the environment where they live. So there's some cold water jellyfish, and if you put them in warm water, it would be outside their natural range. So it would actually probably speed up their metabolism so much it would kill them, right? Because so every species has sort of a range of temperatures that they're most well adapted for. And that's not just jellyfish, it's all species. But the reason why is because, the reason why metabolism in general gets sped up in warmer temperatures is because metabolism is really the function of molecules, right? And they have a natural vibration. And so they move around the cells in large part by just wiggling. And so that wiggling happens faster. So they find more of the molecules they need to break apart or put together, depending on what their job is. So everything just happens faster at higher temperatures. And so that's why metabolism will speed up at higher temperatures. It's kind of just like there's more energy there. So it's a thermodynamic truth that things happen faster at higher temperatures. But if the animal isn't able to take advantage of things happening faster, it could kill it. And that's why animals have certain ranges of temperatures which they've evolved to live in. Was that kind of a clear explanation? Okay.
Makes sense. Another, why do jellyfish do certain things? Why do jellyfish thrive in low oxygen levels?
Yeah, so I wouldn't necessarily say they thrive. It's more that they can handle it better than other animals can. And again, it goes back to metabolism. First thing is the amount of a jellyfish that's actually metabolizing is very small compared to how big it is, because it just has a layer of cells around the outside and a layer of cells, that covers its gut on the inside. The rest of it is jelly, and that jelly is not made out of cells. It's made out of gelatin, and so it doesn't use a ton of oxygen. The only parts that are really using a ton of oxygen are the cellular parts. So it's kind of like cells painted onto a jelly inside that isn't have a very high metabolic demand. So if you take a jellyfish and put it in a low oxygen zone, and then you take a crab and put it in a low oxygen zone, the crab, and they're the same size, say they're the same volume, but the whole inside of the crab is made up of cells that requires oxygen. So it's going to run out of oxygen way faster than the jellyfish. So that's the biggest reason. The second reason is actually the jellyfish can control the gases that are inside of its jelly center. So it can pump oxygen in there and then take that into the low oxygen zone and then use up the oxygen from its mesoglea. That's the inside. That's what the jelly's called, the technical name for it, while it's in the low oxygen zone. And so buy itself a little more time, almost like having a scuba tank with it. So it has two reasons why it can do better in a low oxygen zone than something like a crab or a fish that has just generally higher metabolism.
Does the jelly have stinging cells in it?
No, the stinging cells are really concentrated on the tentacles, and mostly on the tentacles, but sometimes on the underside also, and the oral arms. So the mouth of the jellyfish is underneath, and then instead of lips, it's kind of extended lips. So they're called oral arms. And those are full of stinging cells, and then the tentacles, which are usually around the edge of the bell, those are full of stinging cells also. But usually that's why you can pet the moon jellies on top, because first of all, moon jellies don't really sting us too much, But most of the time, jellyfish don't really have stinging cells up on the top of them. They're all underneath, because that makes sense. Like, if you sting a phytoplankton up on top of your head, it's hard. It's a lot harder to get it around to your mouth. But if it's already underneath you, you can just kind of pull it into your mouth. Yeah.
So the people at the touch tank were like, you can touch them, just don't lick them.
Yeah, that's so funny. Yeah, jellyfish scientists have this funny way to characterize like how bad of a sting it is. Mm-hmm. So like, if it touches you, if you touch it and it stings, that's bad. But if you have to lick it and it stings, then it's not so bad.
It's like a hot pepper.
Yeah, it's kind of like one of those hot pepper tests. Yeah, yeah. But yeah, the sting is it's a really interesting part of the jellyfish. Yeah.
Why are jellyfish adapted to survive in all these extreme conditions, like low oxygen? Is there a reason for that?
Well,
or is that just why? It's just how?
Yeah, we could think of. Oh, thank you. If you think about it, like our planet, the jellyfish have been here for maybe 650 million years, like the oldest animal, one of the oldest animals to still be with us on this planet. So they have gone through a pretty incredible selection process. Like the oceans have been really, really, really cold before. And they've been really, really hot before. And they've been really acidic before. And they've had low oxygen before. So the jellyfish have made it through all those things that could have made them go extinct, because they have all these flexible ways to respond to the environment. So it's almost like they wouldn't be here if they couldn't do what they do. The world has already put them through these incredible selection process. So I said to one of the robotics scientists, I'm like, how come jellyfish turn out to be such efficient swimmers? Like the most efficient, they use the most energy to move of anything they looked at. And the scientist said it's the other way around. Like, they wouldn't be here if they weren't so efficient.
Because they like suck the water in with their tentacles. And
they create a low pressure. Yeah, they create low pressure above. Yeah. So they get sucked through the water rather than pushing against the water. They create a low pressure that pulls them through the water.
So they don't use much energy.
They use the energy and move of any animal that has been studied. They don't move super fast. But they're like, they're like a smart car or something. One of those cars that uses hardly any gas to move. Yeah. Ooh, look at the color of that.
Why did you decide to write a book about jellyfish?
I got really interested in the jellyfish. Like I kind of said this in the book because I was working on this article for National Geographic about ocean acidification. And in the article, it said jellyfish would be winners in a future acidified ocean. But then when I went and looked in the scientific literature, it turned out only 2 experiments had been done to justify that statement. And I was like, really? What else don't we know about jellyfish that we think we know? And I started looking more into what the scientists had been writing about, and it turned out, first of all, what you were saying, like their numbers are increasing, well, or at least it looked like maybe they were, but our baseline, our understanding of jellyfish, they've been so ignored by the scientific community that we couldn't really say what was happening. And there were like all these fights going on about that, and at the same time, people were doing genetics on jellyfish and discovering all these new species of them, and they were trying to make robotic jellyfish. And almost every kind of question I had about jellyfish, it turned out there was just so much that hadn't been explored. I felt like it was worthy of a book to try to understand what jellyfish are and how come they're so amazing. it wasn't just a short article. There was too much to talk about.